Something is missing off the coast of Japan. Not a building, not a ship, an earthquake. 36 hours ago, a magnitude 7.5 ruptured the Japan Trench off Iwate, and since that moment, the ground has been doing something it is not supposed to do. It has been quiet. Too quiet. The aftershocks that should be echoing downward through smaller and smaller magnitudes are thin. The largest one so far sits 2 full magnitude units below what statistical seismology demands. 1,000 times weaker in energy than the rulebook says it should be. A monitoring station in Siberia just recorded an electromagnetic signal physicists cannot explain. The Japan Meteorological Agency has started a 132-hour countdown clock, and they are openly naming 2 precedents, Tōhoku 2011 and Kamchatka 2025, that started exactly like this. Stay with me, because tonight I want to walk you through what the silence actually means, and why the next 3 days may be the most important 3 days in Pacific seismology this decade. Before we begin, if you genuinely enjoy what we do here at Project Nightwatch, hit like and subscribe because this story has 132 hours left on the clock, and we will be here tracking every one of them. Tell me in the comments where you're watching from tonight, and tell me this. 15 years after 2011, Japan poured billions into seawalls, sirens and drills. Every system worked, the ground shook, people ran, and still, with every sensor pointed at this fault, nobody can tell you whether the silence in the aftershocks means it is over, or that the real one is still coming. Did we learn enough? Let me know. Now, let's get into it. Part 1. The silence that broke the model. We are 36 hours past rupture. The initial shaking is over. The tsunami advisories along the Sanriku coast have been downgraded. The helicopters have flown their first damage assessment passes, and the news cycle has already begun to move on because in Japan, a magnitude 7.5 is terrible, but it is not unprecedented. It is the kind of event the country has engineered itself to survive, and for the most part, it did. Buildings swayed and held, trains stopped and restarted. The rhythm of a hardened society absorbed the shock. But in a small, quiet room full of seismologists watching waveforms scroll across monitors in Tsukuba, the mood is not one of relief, it is something closer to unease. Because what they are looking at, or rather what they are not looking at, is a hole in the data where an entire population of earthquakes should be. Let me set the technical scene cleanly before we go any further. The Japan Meteorological Agency recorded this event at magnitude 7.5. The United States Geological Survey, monitoring the same rupture from halfway around the world, logged it at magnitude 7.4. That 1/10th gap might sound like an accounting dispute, but it isn't arbitrary. The JMA magnitude is calibrated specifically for Japanese subduction geometry, using a dense network of sensors located directly above the fault, and for events on the Japan Trench, the JMA number is the one seismologists trust first. So we are treating this as a 7.5. A large earthquake, a significant earthquake, an earthquake that should, by every rule of the trade, be followed by an aftershock sequence with a very specific shape. Here is the shape it should have. There is a principle in seismology called Barth's law, which states that the largest aftershock of a main shock is typically about 1.2 magnitude units smaller than the main shock itself. That is not a guess. That is a statistical regularity observed across tens of thousands of earthquake sequences around the world, in every tectonic setting, on every kind of fault for over half a century. Apply Barth's law to a magnitude 7.5, and you get an expected largest aftershock somewhere around magnitude 6.3. Not exactly, seismology never promises exactly, but in that neighbourhood, plus or minus. What has Japan recorded in the 36 hours since rupture? The largest aftershock so far is a magnitude 5.4. That is not a small deviation. That is a gap of roughly 2.1 magnitude units between what the model expects and what the Earth has delivered. And in earthquake terms, because the magnitude scale is logarithmic, a 2-unit difference is not a factor of 2. It is a factor of 1,000 in energy release. The biggest aftershock so far has released about 1/1000th of the energy it statistically should have. And it gets stranger the deeper you look, because Barth's law is only one piece of the expected aftershock fingerprint. The other piece is something called the Gutenberg-Richter distribution, which describes how earthquakes of different sizes populate a sequence. For every magnitude 6, you expect roughly 10 magnitude 5s. For every magnitude 5, roughly 100 magnitude 4s. For every magnitude 4, around 1,000 magnitude 3s. Earthquakes, in other words, usually echo downward in scale, like a waterfall cascading into smaller and smaller pools, and in that cascade the small ones are the loudest signal of all, because they tell you the fault is still adjusting, still settling, still releasing the little tensions that the big rupture didn't quite resolve. Right now, off the coast of Iwate, that cascade is thin, not absent, not silent, but thin. The small earthquakes that should be filling the waveform record by the hundreds are coming in by the dozens. The seismologists watching this have a phrase for it. They are calling it a deficit, which is a dry bureaucratic word for something that beneath the surface feels genuinely wrong. This matters because of what sits over it. The Japan Meteorological Agency, within hours of the rupture, issued what is formally called a Nankai Trough Mega Quake Advisory, under the protocol that activates whenever a magnitude 7 or greater event occurs in specific zones of elevated concern. That advisory is not a prediction, it is a probability shift. It is the JMA saying officially that the statistical likelihood of another larger earthquake in the following days has risen above the baseline enough to warrant telling the public. The advisory has a fixed duration. It runs for 1 week from issuance. As of right now, there are approximately 132 hours remaining on that clock. And the JMA knows, and the seismologists know, and anyone who has studied the history of the region knows, that this pattern, a large event, followed by an unusually quiet interval, followed by the advisory clock ticking down, is not a pattern that always resolves peacefully. It sometimes resolves the other way. And so the question becomes not whether the ground is shaking, but what the ground is doing in the spaces between the shakes. The problem, in other words, is not what we are seeing, it is what we are not. Part 2. Why this is statistically rare, but not impossible. Let's sit with that 2.1 magnitude gap for a moment, because I want you to feel how unusual it actually is before we talk about what it might mean. Barth's law, as I said, is a statistical regularity, which means it comes with a distribution around it. The expected difference between a main shock and its largest aftershock is 1.2 magnitude units on average, but the actual observed gap varies. Some sequences produce aftershocks nearly as large as the main shock. Some produce aftershocks almost 2 full magnitude units smaller. When you plot thousands of real-world cases, you get something close to a normal distribution around that 1.2 average, with a standard deviation somewhere in the range of half a magnitude unit. A 2.1 gap in statistical terms sits roughly 2 standard deviations out from the mean. That puts the current Japan sequence somewhere in the 1 to 2% tail of all earthquake sequences ever observed. Rare. Not impossible, but rare enough to make a professional seismologist set their coffee down. That's just Barth's law. Layer on top of it the second deviation, the thin, small event population, and the statistical picture gets more uncomfortable. There is a law that governs how aftershock rates decay over time, called Mori's law, which describes the expected drop-off in aftershock frequency in the hours and days after a main shock. The curve is steep at first, then flattens as the sequence matures. If you run Mori's law forward from the moment of rupture and compare it to the actual count of detected events, you get a prediction for how many small earthquakes should have occurred by now. In the Japan trench case, the real count is running under that prediction. Not catastrophically under, but consistently under, hour after hour, in a way that starts to look systematic rather than random. And there is a third piece of the fingerprint I haven't named yet, which is something called the B-value. The B-value is the slope of the Gutenberg-Richter line I mentioned earlier, the one that describes how earthquake size distributes itself across the population. In a normal, healthy aftershock sequence, the B-value sits close to 1, meaning the ratio of small events to large events follows a specific, well-understood proportion. When the B-value drops below 1, it means the sequence is producing proportionally more large events and fewer small ones, which is a signature that seismologists have historically associated, with some controversy, with foreshock sequences. When the B-value is anomalous, the sequence is, at a minimum, behaving in a way that is worth watching carefully. The Japan trench sequence right now has a B-value that is drifting in exactly that direction. Not alarmingly, not conclusively, but enough to add a third line of evidence to the file. So we have 3 statistical features, all pointing in the same direction, all pointing toward a sequence that is behaving at the edge of what models consider normal. And when I say edge, I mean it. Every one of these deviations, taken alone, would fall within the range of things that occasionally happen in earthquake sequences. The world sees low aftershock main shock sometimes. The world sees slightly anomalous B values sometimes. The world sees sequences that run under Omori's prediction sometimes. What makes this case interesting is the convergence. 3 independent statistical measures, all slightly off in the same direction, all clustered around the same fault segment at the same time. That convergence is what drags the probability of pure coincidence downward from comfortable to uncomfortable. Here is what I want you to hold on to, though, because this is where the science demands discipline. Rare does not mean impossible. Rare does not mean meaningful. Rare, in a planet with hundreds of earthquakes a day and thousands of aftershock sequences recorded over the last century, happens constantly. The fact that something sits in the 1% tail of a distribution does not automatically make it a precursor to anything. It can just be an edge of distribution event, the kind of outlier that statistics guarantees will occur somewhere, at some point, and which carries no special predictive weight by itself. Seismologists have been burned too many times by reading meaning into statistical tales. The history of earthquake prediction is a history of false alarms built on exactly this kind of reasoning. But edge of distribution events are also where surprises come from. They are, almost by definition, the region where our models are least tested, least constrained, least sure of themselves. When the Earth produces a sequence that fits neatly in the bulk of the distribution, we know roughly what comes next, because we have seen thousands of similar sequences and we know how they end. When the Earth produces something in the thin edges, we are navigating by extrapolation. We are assuming the patterns we learned from the common cases apply to the uncommon ones, and sometimes they do, and sometimes they don't. And the only way to tell the difference is to wait and watch and see which of several possible futures the ground actually delivers. Which brings us to a question that has to be asked before we go any further, because otherwise we are building a whole argument on a foundation that might not be real. Is this deficit actually happening, or are we just not seeing the earthquakes that are there? Part 3. The catalogue problem. Is this even real? Here is a fact about seismology that most people don't realise. Every earthquake catalogue in the world is incomplete. Every single one. The smaller the earthquake, the more likely it is to be missed entirely, because small earthquakes produce weak signals that only nearby instruments can detect, and the density of instruments is not infinite. In Japan, the land-based seismic network is one of the most sophisticated in the world, with sensors packed closely enough that almost nothing above magnitude 1 or so gets past them on the Japanese mainland. But the Japan Trench, where this earthquake happened, is not on the mainland. It is offshore, under several kilometres of water, along a subduction zone that runs roughly parallel to the coast, but sits 100 to 200 kilometres out to sea. The sensors that monitor it are a mix of onshore stations straining to hear faint signals at distance, and offshore stations, many of them part of the SNet system, which is an array of seafloor instruments designed specifically to close this blind spot. But even with SNet, the detection threshold offshore is meaningfully higher than it is onshore. Small events get lost in the background noise more easily. Ambient ocean noise, ship traffic, currents, and the basic physics of seismic waves travelling through water all conspire to raise the floor of what can reliably be heard. Seismologists have a technical term for this floor. It is called the magnitude of completeness, usually abbreviated as MC, and it represents the smallest magnitude at which a catalogue can be considered statistically reliable. Below MC, you might catch some events, but you are missing others, and any analysis you do on that part of the catalogue is suspect. Above MC, the catalogue is essentially complete, and the statistics are trustworthy. For the Japan Trench region, MC in routine operations sits somewhere around magnitude 2 to 2.5 offshore, which is already a coarser detection floor than the near real-time MC on land. And here is the wrinkle that matters right now. During active aftershock sequences, MC rises. It rises because when many earthquakes are happening close together in time, their signals overlap on the seismograms, and the smaller events get buried in the waveforms of the larger ones. A magnitude 2 event that would be easy to spot in a quiet week becomes very hard to spot in the first hours after a magnitude 7, because the ground is still ringing with the aftermath of the main rupture, so it is entirely possible that the small earthquakes we think are missing are not missing at all. they might simply be inaudible to our current instruments for the next few days, until the aftershock cacophony dies down enough for the catalogue to catch up. This is a real concern, and any responsible analysis has to take it seriously. It is also not the end of the conversation, because modern seismic catalogues are not just based on human analysts squinting at waveforms. They are built with automated detection algorithms, waveform cross-correlation techniques, and increasingly, machine learning systems trained to pick out weak events from noisy backgrounds. Those systems are running right now. They are processing the data from the last 36 hours as fast as the computers can chew through it. And the preliminary picture they are producing, even accounting for expected catalogue incompleteness, in the immediate post-main shock window, still shows a deficit. Not as dramatic a deficit as the raw headline numbers suggest, but a real one. Even when you correct for the known biases, the small earthquakes that should be there are underrepresented. There is another complication worth flagging. The JMA catalogue and the USGS catalogue do not always agree on the count of small events, because they use different detection networks, different algorithms, and different reporting priorities. In the first hours after a major event, both agencies focus their analytical effort on the large earthquakes first, because those are the ones that matter for public safety, tsunami warnings, and infrastructure response. The smaller events get queued for processing later, which means the catalogues fill in progressively over hours and days after the initial rupture. Right now, 36 hours in, the catalogues are still maturing. Events that happened in the first 6 hours are now being added that were not visible in the first public releases. That process will continue for days, so some of what looks like a deficit right now may resolve itself as the catalogue backlog gets processed. But here is the thing. Seismologists who work this region know these dynamics intimately. They have been running earthquake sequences through exactly this kind of evolving catalogue for decades. They know how much filling in to expect in the first 72 hours, and they know how to estimate the deficit against that expected filling rate. And the ones who are watching this sequence right now, the people who spend their careers staring at Japan trench seismograms, are not saying the deficit is purely an artifact of incomplete reporting. They are saying it looks real, even after you adjust for the catalogue effects, even after you account for the offshore detection flaw, even after you wait for the automated systems to catch up. It might shrink as more data comes in, it almost certainly will shrink somewhat. But it is unlikely to vanish entirely, which leaves us with the core question in its sharpest form. Are the aftershocks absent, or are they just hidden? And if they are absent, what does that absence actually mean? Part 4. The first fork in the road. There are, broadly speaking, two ways to explain what the Japan trench sequence is showing us, and the uncomfortable truth is that both explanations fit the data we have right now equally well. They make identical predictions for the first 36 hours. They only begin to diverge in the hours and days ahead, which means we're standing at a fork in the road, and we cannot yet tell which path the Earth has chosen, and the only way we will find out is to wait for the ground to tell us. The first explanation, which I'll call Model A, is the optimistic one. It goes like this. The magnitude 7.5 earthquake was an efficient rupture. It broke a section of fault cleanly, released the stress that had been building up along that section, and did so in a way that left very little residual strain to produce strong aftershocks. Some faults, depending on their geometry, their roughness, their frictional properties, and the way stress was distributed along them before the rupture, can break in a way that is almost complete in a single event. When that happens, the aftershock sequence is naturally muted, because there simply isn't much leftover stress to drive it. A low aftershock count in this reading is not a warning. It is a sign that the fault did its job. The system is stabilizing. The Earth released what it needed to release. The next few days will see the sequence gradually decay toward background levels. The catalogue will catch up to its thin but real population of small events, and a few weeks from now, this will be remembered as a significant earthquake that was followed by a remarkably quiet aftermath. A statistical curiosity but not a catastrophe. The second explanation, Model B, is the one that keeps seismologists awake at night. In this reading, the rupture was not complete. The magnitude 7.5 broke part of a larger locked region, but left an adjacent section of fault intact. And when a rupture stops partway across a region of built-up stress, it does not simply leave that remaining stress untouched. It redistributes it. Physics requires that the forces that were being held back by the broken section have to go somewhere, and where they go is into the surrounding crust, concentrating additional load onto whatever pieces of the fault are still locked. That concentration can push previously stable sections closer to their breaking point. In this model, the reason the aftershock sequence is thin is not because the stress has been released. It is because the stress has been transferred. It has moved from one part of the fault, the part that just broke, to another part, the part that has not broken yet. And faults that are approaching failure, under certain conditions, can be quieter in the short term than faults that have just slipped, because the stress concentration is happening on a relatively narrow region that is not yet producing widespread microfracturing. The word seismologists use for these locked regions is asperity. An asperity is a patch on a fault that is stuck, held in place by friction, while the surrounding fault may be slipping slowly or not at all. Asperities are where the energy of major earthquakes is stored. When one breaks, it can break entirely, releasing the stress in a single cataclysmic rupture. Or it can break partially, with the rupture stopping at an internal boundary and leaving an adjacent patch still loaded. In the Japan Trench, the fault is understood to be made up of multiple asperities of varying size and depth, some of which have ruptured in living memory, some of which have not. The question Model B raises is whether the magnitude 7.5 we just experienced was the breaking of a relatively small asperity, sitting next to a much larger, still intact one, and whether the stress released by the smaller break has been quietly loaded onto the larger one. Here is the difficulty, and the thing that makes the next 72 hours so consequential. Both models produce the same signature right now. In the first day and a half after rupture, a completed rupture with low residual stress looks statistically identical to an incomplete rupture with transferred stress. Both can produce a thin aftershock sequence. Both can produce an anomalously small largest aftershock. Both can produce a B-value drift. The things that distinguish them are the things that happen next. A completed rupture will see its already thin sequence decay steadily toward nothing. An incomplete rupture, with stress transferred to an adjacent patch, will eventually produce new activity in a different location, or a burst of moderate events as the stressed patch begins to fail, or in the worst case, a second, larger main shock as the transferred stress exceeds the strength of the loaded asperity. The 72 hours ahead of us is the window in which these two futures separate. If we see continued silence, and the existing sequence decays cleanly, Model A gains ground. If we see activity migrating to new locations, or a moderate magnitude event appearing on a previously quiet fault segment, or a burst of small tremors clustering on the edges of the ruptured zone, Model B comes into focus, and if Model B comes into focus hard enough, fast enough, the JMA advisory that is currently a probability shift might become something more urgent. The Earth, in other words, has not yet told us which model is correct. We are watching a test in real time, and the test will resolve itself whether we are ready for it or not. Which is why, before we talk about what the next 3 days might reveal, we have to look backward. Because we have seen patterns like this before, and when we have seen them, they have sometimes ended in ways that we did not want them to end. Part 5. The precedent. Everyone is thinking about. There is a reason the Japan Meteorological Agency was willing to issue a megaquake advisory within hours of this earthquake, and it is not because the numbers slightly exceeded a statistical threshold. It is because Japan and the international seismological community has lived through two sequences in the last 15 years that started almost exactly this way, and the agency and its scientists are not in the mood to be surprised again. The first is the one every Japanese seismologist carries in the back of their mind at all times, which is the Tōhoku sequence of March 2011. On March 9th of that year, a magnitude 7.3 earthquake occurred off the coast of northeastern Japan, in roughly the same tectonic setting as the event we are discussing now. At the time, it was treated as a significant but manageable earthquake. It produced an aftershock sequence that included several magnitude 6 events. There were conversations among scientists, quiet conversations, about whether the sequence might be a foreshock pattern. Those conversations did not reach the general public. There was no public advisory equivalent to the one JMA operates now, because the megaquake advisory protocol had not yet been created. And 2 days later, on March 11th, the Pacific Plate failed catastrophically along a section of the Japan Trench, more than 400 kilometers long, producing a magnitude 9.1 earthquake and a tsunami that killed nearly 20,000 people and triggered the Fukushima nuclear disaster. The March 9th event, in retrospect, was a foreshock. It was not recognised as one at the time. It was only recognised as one after the main shock arrived and rewrote the interpretation of everything that had come before. The second is more recent and more relevant to how the JMA is currently thinking, which is the Kamchatka sequence of July 2025. Kamchatka is the peninsula in the Russian Far East that sits at the northern end of the Pacific Ring of Fire, along the same megathrust system that eventually feeds down into Japan. Last July, a magnitude 7.4 earthquake occurred in the region. It produced an aftershock sequence that initially looked manageable, though already showing some statistical oddities. Then, days later, a magnitude 8.8 earthquake ruptured a much larger section of the same subduction zone. That event was, in energy terms, the largest earthquake of the 21st century at that point. And again, the smaller event that preceded it was only recognised as a foreshock in hindsight. The pattern, in each case, was the same. A magnitude 7 class earthquake sitting in a region that was already under suspicion for accumulated stress, followed by days rather than hours of unusual quiet, followed by a much larger failure. When JMA looks at the current Japan trench sequence, these are the two cases that define the left edge of the probability distribution they are trying to think through. The question they are forced to ask is not whether the current event resembles those precedents exactly, because every earthquake sequence is different in its details. The question is whether the current event resembles them enough to warrant the same kind of heightened concern. And the honest answer is that it resembles them in some ways and differs in others. The magnitude range matches. 7.5, 7.3, 7.4, these are all members of the same class of events. The temporal placement matches, in the sense that we are now in the same day scale window during which the Tōhoku and Kamchatka sequences revealed themselves as foreshock patterns. The tectonic setting matches, because the Japan Trench is part of the same global megathrust system that produced the two historical precedents. What does not match, at least not yet, is the thing seismologists look for most carefully in these situations, which is spatial migration. In both the Tōhoku and Kamchatka foreshock sequences, there was evidence, visible in retrospect, of seismic activity migrating along the fault in the days before the main shock. The epicenters of the smaller events were not static, they were slowly moving, suggesting that stress was propagating along the fault toward the patch that would eventually fail. We are not yet seeing that kind of migration in the Japan Trench sequence. The aftershocks that do exist are clustering more or less around the location of the original rupture, without showing clear directional drift. That absence is, depending on how you read it, either reassuring or simply premature. Reassuring if you believe migration is a necessary precondition for a follow-up event. Premature if you believe migration can begin at any point in the next several days, because the window during which it could appear has not yet closed. History, the old saying goes, does not repeat. But under pressure, it rhymes, and right now, we are listening very carefully to whether the rhyme is forming, because the current anomaly, the thin aftershocks, the low largest aftershock magnitude, the drifting B-value, all of that fits inside the envelope of what a pre-main shock sequence might look like in its early hours. It also fits inside the envelope of what a simple, unusually quiet aftermath might look like. And the only thing that will tell us which envelope we're inside is time, plus one other element we need to understand clearly, which is how probability itself works in this specific kind of problem. Part 6. Foreshock identification. Is a Bayesian problem. Here is a fact that sounds counterintuitive the first time you hear it, but which sits at the centre of everything the JMA is trying to communicate right now. Most earthquakes are not foreshocks. Almost all earthquakes, in fact, are just earthquakes. They happen, they produce their aftershock sequence, and the world moves on. Foreshocks, defined as earthquakes that precede and are followed by a larger event on the same fault, are rare. In the global seismological record, roughly 1 in 20 to 1 in 100 moderate to large earthquakes turns out to retrospectively qualify as a foreshock, depending on how strictly you define the category and which region you're studying. So when you hear that a magnitude 7 class earthquake has a non-zero probability of being a foreshock for something larger, the actual number behind that statement is small. Not negligible, but small. JMA's working estimate for the current situation sits at roughly 1%. That is the probability they're operating with, give or take, when they decide whether to issue a megaquake advisory. 1%. One chance in 100 that this magnitude 7.5 was the prelude to a magnitude 8 or greater in the next week. And the question you, sitting at home, might reasonably ask is this: why on earth would you issue a public advisory for a 1% probability? Isn't that almost certainly a false alarm? The answer is where the Bayesian logic comes in, and where a lot of intuitions about probability break down. 1% is low compared to 50%. It is astronomically high compared to the baseline. In any given week, the probability of a magnitude 8 earthquake occurring in the Japan Trench region is on the order of a few hundredths of a percent, depending on how you calculate background seismicity. So when the JMA says the current situation carries a 1% foreshock probability, they are saying that the occurrence of the magnitude 7.5 has multiplied the baseline probability of a follow-up main shock by a factor of roughly 20 to 100. That is not a false alarm. That is a legitimate, mathematically significant shift in the risk landscape. It is the Bayesian update, the revision of prior beliefs based on new evidence, and in a region where the consequences of being wrong in the direction of complacency are measured in tens of thousands of lives, a 20-fold probability increase is exactly the kind of thing that justifies a public communication. This is where human risk perception tends to fail, and it is worth pausing on, because understanding why is genuinely important. People hear 1% and interpret it as zero. They reason, not unreasonably in everyday life, that a 1 in 100 event is something you can ignore. You would not take serious precautions against a 1 in 100 chance of rain on your barbecue. You would not change your travel plans over a 1 in 100 chance of a flight delay. So why change anything over a 1 in 100 chance of an earthquake? The answer is that probability is not the only input to rational decision-making. Consequence matters too. A 1% chance of a mild inconvenience is not worth worrying about. A 1% chance of a catastrophic event, where catastrophic means thousands of deaths and trillions of yen in damage, is absolutely worth worrying about. It is, in the cold language of decision theory, an expected value calculation, and when the consequence is large enough, even small probabilities deserve serious attention. There is also a phenomenon called the base rate fallacy that is worth naming, because it cuts in the opposite direction from the one I just described. The base rate fallacy is the tendency to focus on the likelihood of a specific event, while ignoring the underlying baseline probability. In the context of foreshocks, the base rate fallacy causes people to say, look, 99% of earthquakes like this one are not foreshocks, so we should ignore the 1%. What that reasoning misses is that we're not in ordinary conditions. We're in conditions where the baseline has already been elevated, where multiple lines of evidence are pointing in the direction of concern, and where the cost of being wrong is enormous. Under those conditions, acting on a 1% probability is not overreaction, it is calibration. The megaquake advisory in this framing is not a warning that something will happen. It is a statement that the probability of something happening has changed enough to be worth everyone's attention. It is a recalibration of the risk level. It asks the public, and the emergency services, and the infrastructure operators to spend a few days being slightly more prepared than usual, to have evacuation plans fresh in mind, to keep emergency supplies accessible, to know the high ground route from wherever they are. It is not an instruction to flee, it is an instruction to be ready, and that kind of calibrated, probability-aware response is exactly what a mature seismological agency should be doing, in a situation where the statistical fingerprint of the current sequence sits in the uncomfortable edge of the distribution. So when you weigh whether this matters, you're not weighing whether the probability is high in absolute terms, you're weighing whether the probability has shifted in a way that requires attention. And on that measure, the answer is unambiguous. It has. Part 7. The missing signature of a foreshock so far. If the magnitude 7.5 is a foreshock in the sense that Tōhoku and Kamchatka had foreshocks, we should expect within the next several days to see specific signatures appear in the data. This is not guesswork. These signatures have been observed, characterized and catalogued across multiple well-studied foreshock sequences, and while they do not appear in every case, they appear often enough that their presence or absence is informative. Right now, across the Japan Trench sequence, most of them are not present, which is either a sign that this sequence is not heading toward a larger failure, or a sign that we are still too early in the process for the signatures to have developed. The first signature is the one I mentioned earlier, spatial migration. In a foreshock sequence that precedes a major rupture, epicenters tend to drift along the fault in the direction of the patch that will eventually break. The drift is usually slow, on the order of kilometers per day, and requires careful analysis to distinguish from random scatter. But it is there, in retrospect, in many of the best documented cases. Right now, in the current Japan trench sequence, the aftershock epicenters are not showing clear migration. They are clustered around the rupture zone, scattered in a pattern that looks more like ordinary post-main shock aftershock distribution than like directional drift. That is an argument in favour of Model A, the completed rupture, at least for now. The second signature is clustering. Foreshock sequences often show temporal clustering, where events arrive in bursts rather than in the smooth decay pattern that Omori's law predicts. A burst of 3 or 4 moderate events over a few hours separated by quiet intervals is a different kind of signal from a steady decay. Right now, the Japan trench sequence is not showing strong clustering. The events that are happening are spread across time in a pattern that is not obviously burst-like. That is, again, an argument against the foreshock interpretation, at least for now. The third signature is the B-value anomaly I mentioned earlier. Foreshock sequences often show B-values that drift downward before the main shock, reflecting a shift in the balance between small and large events. This is the one signature where the Japan trench sequence is showing some evidence of the foreshock pattern. The B-value drift is there, modest, not extreme, but present. So 1 out of 3 known signatures is trending in the direction of concern, while the other 2 are not. That is an ambiguous signal, not a clear one. Why might the absent signatures not yet be present? There is a real possibility, which is that foreshock sequences take time to develop their full character. In the Tōhoku case, the migration pattern was clearest in the final 24 to 36 hours before the main shock, which means that if you had been looking at the sequence at the 36-hour mark after the foreshock, you might not have seen strong migration yet. The absence of migration right now is not evidence that migration will not appear. It is evidence that, at this specific moment, 36 hours after rupture, migration has not yet appeared. Those are different statements, and the difference matters. We might be in the quiet phase before the structure becomes visible, or we might be in a sequence that will never develop that structure, because it is not a foreshock sequence at all. Both possibilities remain open. There is also the problem of real-time detection limits, which we talked about earlier. Migration patterns in particular are sensitive to the precision of event locations, and offshore events are harder to locate precisely than onshore ones. A migration trend that will be visible in 6 months, after the catalogue has been fully reprocessed with careful relocation techniques, may be invisible right now in the preliminary real-time catalogue. The famous Tōhoku foreshock migration, for instance, was much clearer in post-event analysis than it was in real-time monitoring. If the current sequence contains a migration signal, it may not be detectable with the tools we have available right now. We might see it only when the sequence is reprocessed in the coming weeks. There is a principle in science that I want to invoke here, because it applies directly. Absence of evidence is not evidence of absence. The fact that we are not currently seeing clear foreshock signatures is not proof that the sequence is not a foreshock sequence. It is only proof that the signatures, if they exist, have not yet become visible to us. This is a crucial distinction, and one that seismologists understand intuitively, but that does not always translate to public communication. When JMA says the sequence does not yet show clear foreshock patterns, they are not saying it is safe. They are saying the evidence is incomplete, and in a window as consequential as the next 72 hours, incomplete evidence is not a reason for complacency. It is a reason to keep watching. Part 8. The Quiet Asperity Hypothesis. Let me return to the idea of asperities and go deeper into it, because it is the physical mechanism that makes Model B plausible, and understanding it will help you understand why the seismologists who believe in Model B are not being paranoid. They are being consistent with the physics of how faults actually behave. An asperity, as I said earlier, is a locked patch on a fault. The term comes from engineering, where it originally referred to the microscopic bumps and irregularities on 2 surfaces that are pressed together. At small scales, no surface is truly smooth, and when 2 surfaces touch, they only actually make contact at their highest points. Those contact points are the asperities. They are where the friction comes from. They are where the load is concentrated, and on a fault, the same concept applies at a much larger scale. A fault plane is not a perfectly flat surface sliding smoothly past itself. It is a rough, irregular interface, with patches that are stuck and patches that are slipping, with contact points that carry most of the load, and interstitial regions that transfer little force. The stuck patches, the asperities, are where the elastic strain accumulates. They are where the future earthquakes are being stored. The Japan Trench is known to contain multiple asperities of varying size. Some are small, capable of producing magnitude 6 or 7 events when they break. Some are much larger, capable of producing magnitude 8 or 9 events, though they rupture much less frequently. The 2011 Tōhoku earthquake, to give you a scale, ruptured an asperity or a linked set of asperities that was something like 400 kilometers long along the trench. It was enormous. And the surrounding region of the trench still contains smaller asperities that have not yet broken, some of which have been accumulating stress for decades, some of which have been accumulating stress for centuries since the last major rupture in their specific location. What happens, physically, when a magnitude 7.5 earthquake ruptures in this region is that some asperity, or some combination of asperities, has failed. The specific question is which one, and how completely. If the rupture broke a single, well-defined asperity all the way across, and did not load any adjacent ones significantly, then we are in Model A territory. The stress on that patch is gone. The surrounding fault is not dramatically more loaded than it was before. The sequence will decay, and life will go on. But if the rupture broke only part of a larger asperity, or if it broke one asperity and loaded a neighbouring one through the stress redistribution that always accompanies a rupture, then we are in Model B territory. And the key insight of Model B is that the patch that got loaded may not immediately show obvious signs of distress. Asperities, by their nature, are locked. They do not produce small earthquakes easily. The frictional properties that keep them stuck also keep them quiet. When you add stress to an already locked patch, you do not necessarily see a burst of seismicity in response. You may see very little, at least until the stress approaches the breaking point, at which point the asperity fails all at once, catastrophically in a single large event. There is an analogy I want to use because it captures the physics well. Imagine a thick sheet of ice on a pond. If you hit it with a hammer, you can crack it in a few different ways. You can hit it hard enough to shatter the entire sheet, in which case you will see a complicated pattern of small cracks spreading outward from the impact point. That is the completed rupture case. The energy has been distributed across many small failures, and the sheet is now in a thoroughly broken, thoroughly relaxed state. But you can also hit the sheet in a way that causes a single major crack to propagate across part of the ice, stopping somewhere in the middle, with the rest of the sheet remaining intact. In that case, you have released some of the stress, but you have also concentrated the remaining stress at the end of the crack, where it is now loading the still intact ice at higher levels than before. The ice on that side of the sheet may look unchanged. It may not be producing any visible cracks, but it is holding more load than it was a moment ago, and the next failure, when it comes, may be much larger than the first one. That is the quiet asperity hypothesis in its simplest form. The magnitude 7.5 may have cracked the ice partway across, and the silence we are hearing right now may not be the silence of a thoroughly broken sheet. It may be the silence of an intact region that has just been handed an extra share of the load and is holding on to it for now without complaint. The problem for seismologists trying to evaluate this in real time is that the quiet asperity is, by definition, quiet. It does not announce itself with pre-failure seismicity the way some other fault configurations do. It waits, it accumulates, and then, when the threshold is reached, it fails. The only things that might warn us, in the meantime, are subtle signals that are hard to detect, slow slip events that may or may not appear on nearby instrumentation, and the kind of pattern-level anomalies in the overall sequence that the current data is showing, which means we are in a situation where the physics of what might be happening is real, the mechanism is well understood, and the observable signatures may not appear until very close to the moment of failure. If failure comes, the quiet, in other words, may not be calm, it may be incomplete, and the next few days will tell us which. Part 9. The 12 to 13 Hertz Anomaly. Now I want to talk about something that showed up in the data stream shortly before and shortly after the Japan Trench rupture, because it is part of the reason this story has taken on a life of its own online, and because it speaks directly to the question of what, if anything, might herald a large earthquake in the hours before it happens. I also want to be careful with it, because it is exactly the kind of observation that needs to be contextualized rather than dramatized. There is a monitoring station in Tomsk, Siberia, part of a network that tracks electromagnetic activity in the atmosphere. It is not a seismic station in the traditional sense. It is listening to something else, the electromagnetic environment of the Earth, and specifically to the very low frequency and extremely low frequency waves that propagate through the gap between the ground and the ionosphere. That gap, which acts as a resonating cavity, supports a set of standing electromagnetic waves known as Schumann resonances. The first fundamental Schumann resonance sits at around 7.83 Hz, and there are higher harmonics at roughly 14, 20, 26 and 33 Hz. These frequencies are well established, well measured, and the signature of them is visible in essentially every sensitive electromagnetic recording made at the surface of the Earth, anywhere in the world. What the Tomsk station recorded, in the window around the Japan Trench earthquake, was elevated energy in a frequency band centered around 12 to 13 Hz. That is the part that caught people's attention, because 12 to 13 Hz does not correspond to a canonical Schumann resonance. It sits between the first and second harmonics, in a band that should, under normal atmospheric conditions, be relatively quiet. The anomaly appeared before the earthquake, persisted through it, and continued for some time afterward. It was a real signal, in the sense that the instrument recorded real energy at that frequency. The question is what produced it. Here is where I have to pump the brakes, because single-station observations of electromagnetic anomalies have a long and almost entirely unsuccessful history in the field of earthquake prediction. For every anomaly that appeared to correlate with a subsequent earthquake, there are dozens that appeared and then nothing happened. For every correlation that looked compelling in retrospect, there are equally compelling correlations that fell apart under scrutiny. And the fundamental problem with single-station observations is that they cannot distinguish between a signal that is genuinely related to seismic activity and a signal that is produced by something local to the station, something in the instrument itself, or something in the atmospheric conditions of that specific location at that specific time. Without confirmation from other stations in other locations, all we have is one data point, and one data point in a noisy signal environment is not, by itself, strong evidence of anything. So why am I telling you about it at all? Because the story we are trying to tell right now is not only about the seismic data. It is about the broader question of whether the Earth is showing us a pattern that might indicate something bigger is coming, and in that context, the Tomsk anomaly is at least worth acknowledging. Not because it proves anything, it does not, but because if the seismic pattern is already abnormal, the threshold for paying attention to other anomalies, even weak and unconfirmed ones, drops a little. In a universe where the Japan Trench sequence looked perfectly normal, we would ignore the Tomsk reading without a second thought. In a universe where the sequence already looks strange, we file it, we flag it, and we watch to see whether similar readings appear elsewhere. That is the only responsible way to handle a single-station anomaly of this kind. Which is exactly the point where we need to move from the anomaly to the question of why it probably is not what some people are claiming it is, and what nonetheless makes it worth keeping in our peripheral vision. Part 10. Why this is probably noise, but not useless. There is a boring, mundane explanation for almost every electromagnetic anomaly ever detected at a ground station, and it is almost always some version of the same story. Wind blowing across the instrument produces microphonic noise in the sensors. Temperature changes cause the electronics to drift. Nearby lightning, either close enough to directly couple into the antennas, or far enough away that it arrives as a propagated radio wave, produces spurious signals. Power line interference, human-generated radio traffic, solar activity affecting the ionosphere, and the instrument's own internal oscillations all contribute to a background noise floor that constantly contains false positives for any given narrow-band signal you might be looking for. The history of electromagnetic earthquake precursor research is, to put it bluntly, a graveyard of false signals. Stations across the world have reported at various times anomalies that appeared to correlate with subsequent earthquakes. Papers have been published, theories have been developed, and then, when other researchers attempt to replicate the findings, when they look at the same phenomenon across multiple stations or across multiple earthquakes, the signal vanishes. it was an artifact of local conditions or of statistical cherry-picking, or of a narrative that was constructed after the fact to connect unrelated observations. This has happened enough times that the mainstream seismological community is deeply and appropriately skeptical of any single-station electromagnetic anomaly that is claimed as a precursor. The 12 to 13 Hz reading from Tomsk, in this light, has to be treated as almost certainly noise, or at most, as a possibly interesting observation that cannot be elevated to the status of a signal without confirmation from other stations, and as of right now, that confirmation is not there. Other electromagnetic monitoring stations around the world, which would have been recording during the same window, have not reported matching anomalies at that frequency. Which is one of the strongest arguments for treating the Tomsk reading as a local artifact. If the signal were real, if it were produced by something at the scale of a tectonic event on the other side of the Asian continent, it should have appeared on multiple instruments in multiple locations. It did not. And yet, I want to keep a small door open, not because I think the Tomsk reading is meaningful in isolation, but because of what the broader context does to our handling of anomalies. There is a principle in intelligence analysis, borrowed more broadly into pattern recognition work, which is that individual weak signals are usually noise, but correlated weak signals, even when each individually fails to meet a confidence threshold, can be worth attention when they cluster. In a normal week with a normal seismic pattern, the Tomsk anomaly would be filed and forgotten. In this particular week, with a seismic pattern that is already showing statistical oddities, the anomaly is not proof of anything, but it is worth knowing about. It is worth tracking whether similar anomalies are reported from other stations in the coming days. It is worth being aware that if a second large earthquake does occur in the region, the Tomsk data will be re-examined carefully to see whether the pre-event anomaly extends or strengthens. Most anomalies disappear under replication. That is the correct scientific stance. But when the pattern around them is already abnormal, even the anomalies that will probably turn out to be noise deserve a place in the file, because our decision of where to look next is shaped by where the weak signals are already pointing. Part 11. The controversial alternative, LAI coupling. There is a theoretical framework that some researchers have proposed to explain how earthquakes might generate electromagnetic anomalies in the hours or days before they rupture, and it is worth explaining briefly, not because I believe it has been proven, but because it is the scientific backdrop against which anomalies like the Tomsk reading get interpreted. The framework is called lithosphere-atmosphere-ionosphere coupling, usually abbreviated as LAI coupling, and it is a genuinely interesting, genuinely controversial idea that has had a persistent presence on the edges of seismology for decades. The proposed mechanism goes something like this. Rocks under high stress, particularly the kind of stress that builds up along a fault approaching failure, can release small amounts of radon gas through microfractures. Radon is radioactive. It produces alpha particles as it decays. Alpha particles ionize the air. Ionized air conducts electricity differently from neutral air. The changed conductivity of the local atmosphere modifies the electromagnetic environment, which can, in principle, propagate upward into the ionosphere and produce detectable disturbances in both the atmospheric electric field and the upper atmosphere. The attractiveness of this mechanism is that it provides a physical, non-mystical pathway by which stress building up deep in the crust could produce surface-level electromagnetic signals that might be detected before the earthquake itself happens. It is, in other words, a possible precursor mechanism. The unattractiveness of the framework is that, despite decades of research, it has never produced a reliable, repeatable predictive success. There are individual case studies where researchers have claimed to detect radon anomalies or ionospheric disturbances in advance of specific earthquakes. There are papers showing correlations in specific data sets. And then, when the same methods are applied to different earthquakes, or when the same data sets are reanalyzed with proper statistical controls, the correlations tend to weaken, or to vanish entirely, or to be revealed as products of selection bias in how the original cases were chosen. The literature is a battlefield, with proponents arguing that the mechanism is real, but difficult to detect reliably, and skeptics arguing that the correlations are statistical artifacts produced by the natural tendency of researchers to find patterns when they go looking for them. I will not pretend to resolve that debate here, because it has not been resolved in the scientific literature. What I will say is that the LAI framework is the kind of thing that exists in a particular zone of scientific plausibility, The mechanism is not physically impossible. The component steps, rod-on emission from stressed rocks, ionization of air, electromagnetic effects, are all real phenomena, individually well documented. What is not established is whether the combined effect is strong enough, consistent enough, and predictable enough to be useful as a monitoring tool. And the honest answer, as of today, is that we do not know, and the evidence suggests that even if the effect is real, it is subtle enough that extracting a reliable signal from it requires more than any single station can currently provide. In the context of the current Japan Trench situation, the LAI framework is less a tool for predicting what comes next, and more a reminder that the question of how faults might communicate with their environment before they fail is still open. The theory exists, the proof does not. And what that means for our interpretation of the Tomsk anomaly is that we have a possible mechanism that could, in principle, produce the kind of signal that was observed, but we have no basis for claiming that the mechanism actually did produce this particular signal in this particular case. It is one more piece of context, not an explanation, as we try to make sense of a seismic pattern that is already showing us something unusual. Part 12. Pattern recognition versus pattern illusion. Let's pull back for a moment and talk about something that affects every single one of the observations I've been describing, which is the deep human tendency to find patterns in data, especially when the stakes are high and the emotional weight of the situation is heavy. This tendency is not a flaw in thinking. It is, in most contexts, a feature of cognition that has served human beings extraordinarily well throughout our evolutionary history. We are very good at noticing when things cluster together in ways that might matter. We are very good at connecting observations that seem to rhyme. And in most everyday situations, those skills help us survive and thrive. But in the specific domain of earthquake prediction, the same tendency can lead us badly astray, because the data is noisy, the signals are weak, and the stakes are high enough that we want to see meaning whether or not it is there. There is a phenomenon called retrospective correlation, which is what happens when, after a major event, people comb through the data from the preceding days and find anomalies that, in hindsight, seem like warnings. The Tomsk reading is a good example. If the current Japan Trench sequence ends quietly, with no follow-up main shock, the reading will be forgotten. It will be filed as one more anomaly in the archive, not connected to anything important. If, however, a larger earthquake does occur in the next few days, the Tomsk reading will be revisited, cited, analysed in the context of the subsequent event, and presented as a possible precursor signal. This is not because the reading has changed. The reading is what it is. What changes is the meaning we assign to it, based on what happens afterward. And that retrospective assignment of meaning is a notorious source of false positives in the prediction literature, because it allows researchers to build compelling-looking post hoc narratives around what were, at the time, indistinguishable from random noise events. There is a related problem called the selection effect, or more colourfully, the Texas sharpshooter fallacy. It refers to the practice of looking at a large amount of data, picking out the features that happen to correlate with some outcome of interest, and presenting those features as meaningful, while ignoring the equally numerous features that did not correlate. In electromagnetic precursor research, this is a constant danger. There are hundreds of monitoring stations around the world, each recording dozens of different frequency bands and parameters. At any given moment, somewhere in that vast data stream, there will be anomalies. Random noise guarantees it. If an earthquake happens, you can always find some anomaly somewhere that preceded it, not because the anomaly caused the earthquake or predicted it, but because the probability of finding an anomaly in a large enough dataset is essentially 1. This is why replication matters so much. A single observation of an anomaly before an earthquake is almost worthless as evidence. Multiple independent observations at multiple stations of the same kind of anomaly before multiple different earthquakes is the beginning of evidence. Systematic statistical analysis across hundreds of events, controlling for selection effects and noise, is the minimum bar for claiming a real signal. We are nowhere near that bar with the current Tomsk reading, or with any of the anomalies that have been suggested as indicators that something bigger might be coming. Which is why the discipline of seismology, even while watching a sequence that has real statistical oddities, even while running a megaquake advisory, even while JMA openly invokes the Tōhoku and Kamchatka precedents, refuses to make predictions. The discipline is, in effect, saying, we see the pattern, we acknowledge the anomalies, We recognize the resemblance to past events that ended badly, and we will not tell you it means anything specific about what comes next. Because the history of making confident predictions from patterns like this is a history of being wrong. The signal exists in a narrow statistical sense. The meaning does not, or at least we cannot, extract the meaning from the signal with any reliability. So what do you do then, when the seismic pattern is showing you something, and the electromagnetic data is ambiguous, and the statistical anomalies are real but insufficient? You look at everything else. You look at the ground itself, at other points along the plate boundary, at events that might or might not be related but that are at least worth watching. Which is where the next piece of this story comes in, because the same day the Japan Trench ruptured, something else happened 1,500 kilometers away, and it may be meaningful, or it may be coincidence, and we need to know the difference. Part 13. The deep event at the Nankai Trough. On the same day as the Japan Trench rupture, a magnitude 4.0 earthquake was recorded at a depth of about 326 kilometers beneath the Nankai Trough region, roughly 1,500 kilometers southwest of the Iwate rupture zone. That is a deep earthquake. That is well into the intraslab regime, meaning the earthquake occurred inside the subducting Pacific plate rather than at the megathrust interface where the plates meet. Intraslab earthquakes are mechanistically different from megathrust earthquakes. They happen at much greater depths. They are usually not directly connected to the shallower seismic hazard of the subduction zone. And a magnitude 4 by itself is a small earthquake, nothing that would normally make headlines. What makes this particular event worth flagging is the location. The Nankai Trough contains several segments of megathrust fault that have historically produced massive earthquakes on centennial timescales, and one segment, sometimes called Section E, or the easternmost segment of the Nankai system, has not ruptured in the historical record. It is a region of acknowledged, accumulated stress, and Japanese seismologists have watched it for decades as a likely location for a future great earthquake. A small, deep event beneath that specific region, in the same 24-hour window as a major event 1,500 kilometers to the north, is exactly the kind of coincidence that demands a moment of attention, even if it is almost certainly just coincidence. We will return to the mechanics of whether events this far apart can actually influence each other. For now, the point is simply this. A deep, small earthquake beneath an already suspect segment of an adjacent subduction zone, on the same day as the largest Japan Trench event in years, is the kind of data point that seismologists notice. They notice it, they flag it, they add it to the watch list, and then they try very carefully not to overinterpret it. Because the Earth is always producing small earthquakes everywhere, and finding a small earthquake somewhere interesting on the same day as a big one is not, by itself, evidence of causation. But in a week where the central pattern is already abnormal, it becomes one more piece of the file we are building, one more reason to keep our attention distributed across the entire plate boundary, rather than focused narrowly on the rupture zone. Part 14. Dynamic versus static stress transfer. This brings us to a real physics question, which is whether earthquakes can influence each other across large distances, and if so, how? The honest answer is yes, but with heavy qualifications that depend on what kind of influence we're talking about. There are two main ways earthquakes can transfer stress to other parts of the crust, and they operate on very different scales. The first is called static stress change, which refers to the permanent alteration of the stress field around a fault after it has ruptured. When a fault slips, the stresses on the surrounding rock redistribute themselves, with some regions experiencing reduced stress and others experiencing increased stress. This effect is calculable, mappable, and generally well understood. It is also strongly dependent on distance. The stress changes caused by a moderate earthquake fall off quickly with distance, and by the time you're even a few hundred kilometers away from the rupture, the static stress change is negligible, orders of magnitude smaller than the background stress variations in the crust. For a magnitude 7.5 in the Japan Trench to statically stress the Nankai region, 1,500 kilometers away, by any meaningful amount, the physics simply do not work. Static stress transfer across that distance is effectively zero. The second mechanism is called dynamic stress change, and this is the one that is more interesting in the context of what we're seeing. When a fault ruptures, it radiates seismic waves outward through the crust. Those waves carry energy, and as they pass through the rock, they transiently stress and strain everything they encounter. At close range, the dynamic stresses from a large earthquake can be enormous. But unlike static stresses, dynamic stresses do not fall off as steeply with distance. Seismic waves, particularly surface waves that travel along the ground rather than through the deep earth, can carry meaningful amounts of energy across very long distances. And those waves have been documented in multiple well-studied cases to trigger seismicity in distant locations. The 2002 Denali Fault earthquake in Alaska triggered small events in Yellowstone National Park thousands of kilometers away as its surface waves passed through that region. Multiple large earthquakes have been associated with transient increases in seismicity in distant volcanic and geothermal areas. The effect is real, it is repeatable, and it is one of the genuinely surprising features of how the Earth responds to large seismic events. Could the Japan Trench earthquake have triggered the Deep Nankai event through dynamic stress transfer? It is possible, though the details get complicated. Dynamic triggering is most commonly observed at shallow depths, in fluid-rich environments, on faults that are already close to failure. Deep intraslab earthquakes are not the typical target of dynamic triggering, because the physical mechanisms involved, fluid pressure changes and the triggering of faults that are already right at the edge of slipping, are less applicable at depths of 300 kilometers. So while the Japan Trench waves certainly reached the Nankai region, and certainly perturbed the stress field there, the likelihood that those transient stresses caused the specific magnitude 4 event we observed is low. Possible, but low. What the dynamic stress framework really tells us is that earthquakes can, in principle, talk to each other across long distances. The conversation is usually brief, limited to the passing of seismic waves, and limited in its triggering effect to faults that were already approaching failure independently. But the conversation exists, and in some circumstances it matters, and it means we cannot rule out the possibility that the Nankai event was, in some tenuous way, related to the Japan Trench rupture. What the dynamic stress framework does not tell us is whether either event is a signal of something larger coming. Triggered earthquakes, when they happen, tend to be small events that would have happened eventually anyway, just slightly sooner than they would have on their own. They are not usually precursors to major ruptures. They are more like accelerations of the background seismic calendar by a few weeks or months. So while the Nankai event is interesting, and while it deserves its place in the file, the most likely interpretation is that it is a small earthquake that might have been dynamically nudged by the Japan Trench waves, but which does not by itself imply that the Nankai system is about to fail. Earthquakes can talk across distances, in other words, but briefly, and the conversation we observed this week so far does not appear to be loud enough to be diagnostic. Part 15. Kamchatka Reactivation. While we are surveying the broader plate boundary, there is one more observation to add to the file. In the days around the Japan Trench rupture, seismologists also noted some elevated activity in the Kamchatka region, in the area that produced the magnitude 8.8 earthquake in 2025 that I referenced earlier. The activity is not large, it is not a main shock sequence. It is the kind of modest seismic activity that the region produces regularly, and which, on any other week, would be unremarkable. The reason it gets mentioned in this specific context is that the Kamchatka region and the Japan Trench region sit on the same vast plate boundary, the interface between the Pacific Plate and the continental crust of northeastern Asia. They are separated by thousands of kilometers, but they are part of the same tectonic system. Whether events in one region can meaningfully influence events in the other is an open question, and probably one where the answer is mostly no, with occasional, weak exceptions at the margins. The fact that Kamchatka is showing some modest activity in the same week as the Japan Trench rupture is probably coincidence. It is the kind of coincidence that happens when two active regions are both in their ongoing seismic cycles, and their activity occasionally overlaps in time without meaningful causal connection. But it is worth noting because the central story we're trying to tell is about whether the silence on the Japan Trench is the sound of stress relief or the sound of stress redistribution. If stress is being redistributed, the question of where it is going matters. And if activity on other parts of the plate boundary is picking up at the same time, even modestly, that is at least compatible with the interpretation that the system is adjusting more broadly than we initially thought. The Kamchatka activity does not prove that. It does not come close to proving that. But it reinforces the ambiguity, the sense that we are looking at a regional picture where several things are happening at once, and we cannot yet tell whether they are connected or simply concurrent. Coincidence is almost always the right answer. Systemic connection is almost always the wrong one. But the almost is why we are still watching. Part 16. Is the Pacific Plate talking to itself? Let me now indulge a broader, more speculative question, not because I want to wander away from the primary story, but because the broader question frames the primary one. The question is whether the Pacific Plate, as a single vast tectonic unit, ever acts in a coordinated way, with different parts of its boundary adjusting together in response to some larger, shared mechanical state. The answer, in the mainstream view, is mostly no. The plate is too large, the mechanical coupling between different parts of its boundary is too weak, and the local conditions at each active region are too different for coordinated behaviour to be expected at any meaningful level. Each region has its own stress state, its own asperity structure, its own history of rupture and reloading, and its own clock ticking down to its next major event. The idea that those clocks could be synchronized by the plate itself is, in the conventional framing, a non-starter. There is no known mechanism by which the plate as a whole could coordinate the timing of earthquakes at its edges. And yet, there are patterns in the global seismic record that have, from time to time, suggested something more than pure regional independence. There are clusters of large earthquakes that occur within relatively short time windows across widely separated regions of the Ring of Fire in numbers that sometimes exceed what random chance would predict. Most of these clusters, when examined carefully, dissolve under statistical analysis. They are the kind of thing that happens when you look at a sufficiently rich data set and find patterns that look meaningful but are actually the expected output of randomness. A few of them survive the analysis, or at least survive in a form that continues to prompt debate, and researchers continue to argue about whether there is any real global synchronization in megathrust activity or whether it is all ultimately coincidence. I bring this up not because I think the current Japan Trench situation is driven by some grand, plate-wide coordinated failure. I do not think that. The evidence does not support it, and the mainstream interpretation is correct in its skepticism. But I bring it up because it affects the tone of our interpretation. The Earth at scale looks connected. Its seismic regions activate and quiet in patterns that, to a human observer, seem to rhyme with each other in ways that feel meaningful. Much of that apparent connection is statistical illusion. Some of it might not be, and the honest stance in the face of a week like this one is to acknowledge both possibilities. In the specific case of the Japan Trench, the broader plate boundary context does not change the primary analysis. The primary analysis is still about what is happening on that specific segment of trench, with that specific rupture, and with that specific aftershock sequence. Everything else, the Nankai event, the Kamchatka activity, the electromagnetic anomaly, the broader plate boundary context, is secondary. It is relevant only to the extent that it helps us calibrate our confidence in the primary interpretation. And what it tells us, taken together, is that the confidence should not be high in either direction. The Earth is doing several unusual things at once, and while most of those things are probably not connected, the combination of them means the situation as a whole deserves attention that a simpler, cleaner picture would not require. Which brings us back to the only data that actually matters, which is the data coming in right now from the Japan Trench sequence itself, and from the clock that is ticking down on the JMA advisory. Part 17. What the JMA is actually saying. Let me spend some time on the Megaquake advisory itself, because there is a lot of confusion about what it is and what it means, and a lot of the confusion stems from the fact that it is a genuinely novel kind of public communication that does not fit neatly into either the category of prediction or the category of reassurance. It is something in between those two categories, and the space in between is a space most governments, most agencies, most institutions of any kind have historically refused to occupy. Japan, after 2011, decided it had to occupy that space anyway, because the alternatives had already been tested and had already failed, and the corpses of that failure were documented in every coastal town from Otsuchi to Nami. The advisory you are hearing about on the news tonight is the direct product of a country looking at its own worst day and deciding quietly and methodically that it was not going to handle the next one the same way. The advisory is formally issued under a protocol that JMA developed in the years after the Tōhoku disaster, specifically because the scientific community and the Japanese government recognized in hindsight that the March 9th, 2011 earthquake had been a foreshock that no one called a foreshock. Let me pause on that, because it is important to understand the weight behind the protocol's existence. In the 48 hours between the March 9th event and the catastrophic rupture of March 11th, there were seismologists in Japan who looked at the data, looked at the aftershock behaviour, and quietly wondered whether something larger might be coming. They did not say so publicly. The institutional structure did not permit it. There was no mechanism by which a probability concern, short of a confirmed prediction, could be communicated to the public in an orderly way. So the concern stayed inside the offices where it was felt. The March 11th earthquake arrived, and nearly 20,000 people died. The protocol that governs the advisory currently active as I record this, the advisory that has 132 hours left on its clock, is the institutional response to that silence. It is the mechanism that did not exist in 2011, built specifically so that the next time something like this happens, the concern does not stay inside the offices. The protocol is triggered automatically when specific conditions are met, most importantly the occurrence of a magnitude 7 or greater earthquake in a zone of elevated concern such as the Japan Trench or the Nankai Trough. The automation matters. The automation means the advisory is not a judgment call made by individual humans under political pressure. It is a threshold condition that, once crossed, activates the communication protocol whether anyone in the agency feels politically comfortable issuing it or not. When those conditions are met, the advisory is issued and it runs for a fixed duration, typically 1 week from issuance. During that window, the JMA and associated agencies communicate with the public about the elevated probability of a larger event, advise preparedness measures, and monitor the ongoing seismic activity intensively. Additional personnel are brought in. Analysis cycles that would normally run daily run hourly. The entire apparatus of Japanese seismology tilts its attention toward the region for the duration of the window, and then, if nothing happens, releases that attention at the end of the week and returns to baseline. Here is what the advisory is not. It is not a prediction that a larger earthquake will occur. It is not a statement that a larger earthquake is likely. It is not a call to evacuate or to flee to higher ground or to take any emergency action beyond what ordinary earthquake-aware living in Japan already requires. It is a probability statement, full stop. It is the JMA saying, transparently and publicly, that the risk level has shifted, that the shift is large enough to be worth telling the public about, and that during the advisory window, people should be slightly more prepared than they usually are. Nothing more, nothing less. The Japanese public, which has lived with earthquake risk as a background condition for generations, understands this intuitively. The international audience watching the news from a distance often does not, which is why you see headlines in certain outlets that frame the advisory as if the JMA is predicting an imminent megaquake. That framing is wrong. That framing is, in fact, precisely the kind of distortion that the advisory protocol was designed to avoid, and the JMA has pushed back against it every time it has appeared. What the advisory is, in its underlying logic, is a deliberate admission of uncertainty with consequences. Sit with that phrase for a moment. A deliberate admission of uncertainty with consequences. The JMA could, in theory, choose to communicate only the high confidence, high probability information it has about earthquakes. In that mode, it would warn people only when it was very confident something was about to happen. That is the posture most agencies in most fields default to, because it is safer institutionally. You do not get blamed for false alarms if you never issue alarms. The problem with that mode is that, in the actual physics of earthquakes, the agency never has that kind of confidence. High-confidence earthquake prediction is not a thing that exists, currently, in the scientific toolkit. Despite decades of research and billions of dollars invested in it around the world, no one has yet developed a method that can reliably predict specific earthquakes in specific locations at specific times. If the JMA waited for certainty, it would never warn anyone about anything. The advisory protocol is an alternative mode, in which the agency communicates meaningful probability shifts, even when those shifts are still relatively low in absolute terms. It trades the occasional false alarm, and there will be false alarms. The honest math guarantees that, for the possibility of sometimes, in some cases, giving people enough warning to save lives. That trade is not a free lunch. It costs the agency credibility every time a false alarm expires quietly. The JMA has decided, with eyes open, that the cost is worth paying. This is a genuinely difficult communication to pull off, and the JMA has worked hard to calibrate the language. The advisory talks about relative risk increases rather than absolute risk levels, because relative increases convey the scientifically meaningful part of the probability shift without triggering the inflation of absolute number panic. It emphasizes preparedness rather than panic. It is careful to note that the most likely outcome by far is that the advisory will expire without any follow-up event, and that ordinary daily life should continue more or less unchanged. But it is also clear that the probability of a follow-up event, while low, is meaningfully higher than it normally would be, and that this is not a situation the public should ignore. The agency is walking a tightrope, in other words, between taking the situation seriously and avoiding the induced panic that could itself cause harm. Induced panic is not a hypothetical concern. It is a well-documented failure mode in emergency communication, responsible for its own deaths in past disasters, when crowds stampeded or highways gridlocked, or supply chains collapsed under pressure that was unnecessary given the actual risk. The JMA's language is engineered, phrase by phrase, to avoid that failure mode while still communicating what needs to be communicated. The advisory exists because uncertainty has consequences. That sentence is doing a lot of work, and I want to unpack it one more time before we move on. Uncertainty, in the context of earthquake science, is not the absence of information. It is a structured statement about the bounds of what we can know. The JMA knows quite precisely that it does not know whether the magnitude 7.5 was a foreshock. The agency can tell you the probability distribution. It can tell you the historical precedents. It can tell you which signatures it is watching for and what each one would imply. What it cannot tell you, and what no agency anywhere in the world can currently tell you, is the answer. The advisory is an attempt to share the weight of that uncertainty with the public in a way that respects their ability to make informed decisions, without pretending to a certainty the science does not possess. It is, to my eye, one of the more mature examples of risk communication in any field, anywhere, and it stands in stark contrast to the more common approach of withholding information until the agency is sure, which in earthquakes has historically meant withholding information until the wave is already at the doorstep and it is far, far too late to do anything about it. Part 18. The 3 signals that will decide everything. We are now standing inside the advisory window with roughly 132 hours remaining on the clock. The question we opened with, whether the silence on the Japan trench is the sound of stress already released, or the signature of stress quietly transferred, will begin to resolve itself over the next 3 days, based on 3 specific signals that seismologists are watching for. Let me walk through each one carefully, because understanding them will help you understand, as the news reports come in hour by hour over the coming days, what to pay attention to, what to discount, and what to treat as genuinely serious. These are not theoretical categories. These are the actual diagnostic criteria that working seismologists in Tsukuba, in Tokyo, in Sendai, in research institutes across the Pacific are using right now, tonight, to decide whether the probability that lives inside that 1% tail is shrinking or growing. This is how the sausage actually gets made. The first signal is, paradoxically, the appearance of a magnitude 6 or greater aftershock. If a magnitude 6 plus aftershock occurs in the immediate rupture zone in the next 72 hours, the interpretation will actually shift toward Model A, the completed rupture. That might sound counterintuitive at first. I want you to sit with that counterintuition for a moment because it matters. A larger aftershock should be more alarming, not less, right? A bigger number should mean bigger danger. That is how our instincts work, and those instincts in most situations serve us well. But this is not most situations. The reason Barth's law predicts a magnitude 6-ish largest aftershock is that a normal, completed rupture produces that kind of event as the natural resolution of the residual stress around the broken fault patch. It is the fault finishing its sentence. It is the system exhaling. The absence of such an event is what is currently making the sequence look anomalous, because a fault that has ruptured cleanly is a fault that almost always produces that trailing event within the first few days, and we have not seen it. If one appears, if the sequence finally produces its expected largest aftershock, even a few days late, then the statistical anomaly goes away. the sequence starts to look like a normal bath-compliant aftermath, and the case for Model B weakens significantly. A magnitude 6 in the rupture zone would be Bath's law arriving late, and that would be paradoxically reassuring. It would be the system behaving as the models predict. The uncomfortable silence would end. The unfinished sentence would be finished. News reports in the coming days may describe that event as a dangerous escalation. If it happens in the original rupture zone, and it happens alone, the seismologist watching it will feel something closer to relief. That is how inverted the logic of this situation actually is. The second signal is migration, and migration is the one I want you to watch for most carefully, because it is the signature that connects this sequence directly to the precedents we spent earlier parts of this video discussing. If new seismic activity appears in locations away from the original rupture zone, particularly if those locations form a pattern of progressive drift along the trench or toward adjacent fault segments, that is a signature of stress transfer. It would mean the rupture is not settling down in place, but propagating its effects along the fault in ways that are loading new regions. In the worst case, migration toward a previously locked asperity, especially toward the larger, still intact patches that Japanese seismologists have been quietly mapping for decades, could indicate that the system is setting up for a larger failure. The exact kind of failure that happened in 2011. The exact kind that happened off Kamchatka in 2025. Seismologists will be watching the spatial distribution of events extremely carefully, running nightly recalculations comparing each new epicenter to the previous day's cluster, looking for the drift that, in retrospect, both Tōhoku and Kamchatka showed in the days before their main shocks. Any consistent directional drift, any clustering at new locations that were quiet before the rupture, any evidence that the activity is not simply decaying around the original zone but spreading outward like a fuse burning towards something, will be treated as a serious red flag. If you see a news report in the next 3 days mentioning that aftershocks are appearing in new parts of the trench, that is the signal to pay close attention. That is the one that changes the math. The third signal is the hardest one to sit with, because it is not really a signal at all. It is continued silence. If the aftershock sequence does not produce a magnitude 6, does not show migration, and simply continues to decay along its current anomalously thin trajectory, that is the most ambiguous outcome of all. It does not resolve toward Model A because the expected Bath's law aftershock has not appeared. It does not resolve toward Model B because the expected stress transfer signatures have not appeared either. It leaves us suspended in a middle zone where the pattern remains abnormal but nothing has escalated, where the advisory clock ticks down to 0 without a clear answer, where the seismologists close their laptops on the morning of day 7 and realise they have lived through something unusual without ever being able to name what it was. In that scenario, the megaquake advisory will expire at the end of its 1-week window with the situation still unresolved, and seismologists will spend the following weeks and months analysing what actually happened and why. Papers will get written. Conference sessions will be scheduled. Journalists will ask, reasonably, whether the anomaly meant anything at all, and the honest answer will be, we're not sure. Continued silence is the outcome in which the anomaly deepens rather than resolves, in which the uncomfortable suspicion that something unusual is going on never gets confirmed or refuted by a follow-up event. It is the scientifically messy outcome, the one that does not fit neatly into either model, the one that haunts the literature for years afterward, and it is entirely possible. Maybe the most possible of the three, if I am being honest with you. These 3 signals will play out in some combination over the next 3 days, and I want you to hold something clearly in your mind as we head into this window. We are, in a very literal sense, inside the experiment, not watching an experiment, inside one. The Earth is the apparatus, the fault is the test, the clock is the measurement window, and unlike every laboratory experiment ever conducted, this one cannot be rerun if the result is unclear. The Earth is going to produce data at its own pace, and the data will favour one interpretation over the others, and there is nothing we can do to speed it up or slow it down or repeat it under cleaner conditions. We watch, we record, we update our probabilities, we pay attention to the news cycle, not because the news cycle knows anything the seismologists do not, but because the news cycle will reflect, in real time, which of these 3 signals the ground has chosen to send. And when the signal comes, whichever one it is, we will look back at this moment, right now, 36 hours in, and we will know something about what this earthquake actually was that we cannot know tonight. And we hope, all of us, the researchers and the residents and the viewers and the ones counting down the hours in Iwate and Miyagi and Fukushima, that the resolution, when it comes, is the quiet one and not the loud one. That the magnitude 6 aftershock arrives in the rupture zone, late but arriving, and closes the statistical gap. That the migration never appears. That the silence, if it deepens into something that can be studied at leisure rather than fled from in haste. Because we have been through the loud version before, in the footage from Sendai and Kesennuma and Minami Sanriku, and once was enough for several lifetimes. The question that remains, and that we cannot yet answer, is which version of this story the next 72 hours are about to write. Part 19. The solar factor, low confidence, high curiosity. There is one more variable I want to flag before we bring this home, not because I believe it is driving anything, and not because I am about to make a case for it, but because this is Project Nightwatch, and we do not shy away from naming the things that sit in the uncomfortable zone between conventional science and the questions mainstream science has not fully resolved. In the same window as the Japan Trench rupture, solar wind speeds have been running elevated, in the range of 500 kilometers per second and somewhat higher, with occasional gusts pushing above 600. There has been a minor geomagnetic storm, not a severe one, not one that would light up the northern skies or disrupt satellite operations in any meaningful way, but a real disturbance in the Earth's magnetic field associated with a coronal hole on the Sun. That coronal hole has been rotating toward a geo-effective position for several days, spraying the inner solar system with a steady stream of faster than average solar wind, and the Earth has been sitting in that stream as this earthquake unfolded. Whether any of that has anything to do with what happened off Iwate is a genuinely unresolved question, and I am going to tell you exactly why that question refuses to die in the scientific literature, even after decades of effort to kill it. There is a body of research, some of it serious and peer-reviewed, some of it squarely in the fringe, that has looked at whether solar activity correlates with seismic activity on Earth. The proposed mechanisms, when they are laid out carefully, are not crazy. They involve the way changes in the solar wind and the geomagnetic field might induce small electrical currents in the Earth's crust, the way those currents might interact with the conductive properties of fluids trapped in fault zones, the way perturbations in the upper atmosphere's electromagnetic environment might, in principle, couple downward into the lithosphere and nudge fault systems that are already sitting right at the edge of failure. The key phrase in all of that is already sitting right at the edge of failure. No credible researcher is claiming that solar activity causes earthquakes. The strongest versions of the hypothesis say only that a fault which is otherwise on the verge of slipping, a fault that would have ruptured in a few days or a few weeks regardless, might be nudged across the threshold slightly earlier by an electromagnetic perturbation that would do nothing at all to a stable fault. That is the scientific form of the claim, stated as charitably as I can state it. A trigger, not a cause. A final straw on a camel whose back was already about to break. The correlations found in this research have been, to put it gently, weak and inconsistent. Some studies looking at specific regions and specific time windows report small statistical associations between geomagnetic activity and earthquake timing. Others, looking at different regions or different windows or applying stricter statistical controls, find nothing at all. A number of the early positive findings have been reanalyzed and withdrawn, or have failed to replicate when the same methods are applied to new datasets. A handful of positive findings have survived, or at least survived in a form that continues to prompt debate rather than being definitively dismissed. The honest summary of the literature as of tonight is that if there is any real effect linking solar activity to terrestrial seismicity, it is small, it is subtle, it is inconsistent across regions, and it is nowhere close to strong enough to function as a useful predictor. The mainstream view is that, if there is any effect at all, it lives somewhere below the noise floor of what our current methods can reliably detect. And I am not claiming otherwise. I want to be absolutely crisp about that. The solar activity of the last few days is almost certainly not the reason the Japan Trench ruptured when it did. It is almost certainly not going to drive whatever happens next. If you came here looking for me to tell you that the sun broke Japan, I'm going to disappoint you, because the evidence does not support that claim, and I'm not going to pretend it does. but I mention it because it is part of the background. It is part of the specific set of conditions under which this specific event occurred, and on a channel whose entire premise is that we pay attention to the full environmental context of what is happening above and below our feet. Ignoring the solar state during a week like this one would feel like negligence dressed up as skepticism. The solar wind has been running fast, the magnetic field has been disturbed, the ionosphere has been responding to that disturbance in measurable ways. Somewhere in Siberia, a monitoring station picked up an electromagnetic signal at a frequency that does not correspond to anything physicists formally recognize, and that signal appeared in exactly the kind of electromagnetic environment that a mildly disturbed ionosphere produces. The seismic sequence is behaving anomalously. A deep earthquake fired beneath an unruptured fault segment 1,500 kilometers to the south. These things are almost certainly unconnected, but they're all happening in the same week, on the same planet, under the same sky, and the intellectually honest response is to flag them all and let the listener decide what weight, if any, to assign to the coincidence. Here is the deeper reason I raise it though, and this is where I want to be specific with you. In a situation where we are already flagging multiple low-confidence, high-curiosity anomalies, the aftershock deficit, the Tomsk frequency reading, the Deep Nankai event, the statistical drift in the B-value, adding the solar context is not sensationalism. It is just intellectual honesty. It is saying out loud what seismologists say quietly, which is that the Earth is not a closed system. It is not a laboratory specimen sitting on a shelf. It sits inside a constantly varying electromagnetic environment, bathed in plasma from the sun, modulated by cycles of solar activity that we still do not fully understand. And the question of whether any of that matters for the deep mechanics of fault rupture is, frankly, an open question that has not been closed by decades of inconclusive research. The fact that the mainstream answer is probably not does not make the question illegitimate. It makes the question unfinished. And on a channel that takes unfinished questions seriously, naming the solar context during a seismic anomaly is what we do. What I'm not going to do is build a theory around it. I am not going to claim that the coronal hole caused the earthquake. I am not going to tell you that the elevated solar wind loaded the Japan Trench in some mysterious way, or that the geomagnetic storm is responsible for the missing aftershocks. None of that is supported by the evidence. None of that is going to help you understand what is happening or what might happen next. The solar activity of the last few days is background. It is context. It is a single additional variable in an already complex picture, and it almost certainly plays no meaningful role in the resolution of the next 72 hours. The signals that matter for that resolution are the seismic ones, the three I just walked you through, the magnitude 6 that may or may not arrive, the migration that may or may not appear, the silence that may or may not deepen. Those are where your attention should sit. The sun is, at most, part of the scenery. But I wanted it on the record. No proven mechanism, no reliable prediction, no claim, implicit or explicit, that the solar environment is driving this story. Just one more variable, filed for completeness, logged in the full context view of a week in which the Earth is doing several unusual things at once, and the honest scientific posture is to name all of them, assign each its appropriate weight, and keep our eyes on the signals that actually matter while acknowledging, without embarrassment, that a few of the ones that probably do not matter are worth writing down anyway. Because every now and then in the history of science, the thing that turned out to matter was the thing everyone almost did not bother writing down. And I would rather tell you about a variable that turns out to be irrelevant than stay silent about one that turns out years from now to have been a clue. Part 20. The real ending. Unresolved on purpose. Let me bring us back finally to the question we started with, and to what the next 72 hours will actually tell us, and what they will not. The question was this: is the silence of the small magnitudes the sound of stress relief that is already over, or the signature of something much bigger preparing to fail next? That is the question that sent us down this entire path. That is the question the Japan Meteorological Agency is sitting with right now, in rooms full of monitors and analysts who have not slept properly since the rupture. That is the question every coastal community from Hachinoe down to Sendai is sitting with as they move through their ordinary evenings, pretending for their children that this is an ordinary week, when they know, in the private parts of their minds, that it is not. The honest answer, as of the moment I am recording this, is that we do not know. We have one statistical anomaly that is real and striking, the 2.1 magnitude gap between the main shock and the largest aftershock, which places this sequence in roughly the 1 to 2% tail of observed earthquake sequences. We have a second anomaly, the thin population of small events which reinforces the first. We have a third, modest anomaly, a B-value drift that is trending toward values historically associated with foreshock sequences, but not dramatically so. We have a mega quake advisory running, with 132 hours remaining, invoked on the basis of those anomalies and the historical precedents of Tōhoku and Kamchatka. We have an electromagnetic anomaly from a single station in Siberia that is probably noise. We have a deep intra-slab earthquake at the Nankei Trough that is probably coincidence. We have elevated solar wind speeds that are almost certainly irrelevant. We have, in other words, a situation where most of the individual pieces of evidence are individually weak, but where the combination of them is, at a minimum, distinctive. And that is the word I want you to hold on to as we close. Distinctive. Not alarming, not dismissible, but distinctive. The kind of pattern that does not come along often, and when it does, demands the kind of attention that it is currently getting. The two interpretations that fit this combination are the ones we laid out at the start. Model A, the completed rupture, in which the magnitude 7.5 broke a self-contained asperity, released the stress that had been built up on it, and is now settling down in a sequence that is unusually quiet but statistically still within the distribution of possible outcomes. And Model B, the transferred stress, in which the rupture broke only part of a larger loaded region, shifted stress onto a still intact asperity, and is producing the quiet aftermath we are observing precisely because the newly loaded patch is itself quiet by nature, storing the additional load without announcing it. Both models are physically plausible. Both models are consistent with the data we have. Both models are consistent with the data we do not have. And both models, crucially, predict different futures, which is the only reason this next window matters as much as it does. The 72 hours ahead of us is the window in which these two futures separate. A magnitude 6 aftershock in the rupture zone, arriving late but arriving, pushes us toward Model A. Migration of activity to new locations, or a new moderate event on an adjacent segment, pushes us toward Model B. Continued silence leaves us suspended between them, with the advisory expiring and the seismological community arguing about what it meant for years afterward. Whatever happens, the resolution will come on the Earth's schedule, not ours. The fault will speak when it is ready to speak, and not a moment before, and the best we can do is be in the room when it does. I want to be clear about what this means, and what it does not mean, for you, for me, for anyone who is not living in Japan, and on the line for the decisions that matter most in the coming days. For the people of Iwate and Miyagi and Fukushima, and the coastal communities along the Japan Trench, the situation requires vigilance. Not panic, but vigilance. Know your evacuation route. Keep your emergency supplies accessible. Know the high ground nearest your home, your workplace, your child's school. The JMA is providing you with the best probability calibrated guidance that current science can produce, and the right response is to take it seriously, maintain awareness, and be prepared. The advisory is a gift in its way. It is the scientific establishment being honest about uncertainty in a situation where dishonesty could cost lives. It will, most likely, expire without further incident, and the last 132 hours of elevated awareness will be remembered as a drill, a rehearsal, a week of careful attention that turned out to be unnecessary. That is the most likely outcome. I want to say that clearly. That is the most likely outcome by a considerable margin. But the fact that a follow-up event is not the most likely outcome does not mean it is impossible, and the structure of the advisory is designed to reflect that honest assessment rather than to comfort you with false certainty. For the rest of us, watching from elsewhere, the situation is an opportunity to see, in real time, how modern earthquake science actually works. Not the Hollywood version, with scientists yelling into phones and jagged lines on seismographs that spell doom in 90-point font. The actual version, which is slower, more ambiguous, more statistical, more honest about what it does not know. The Earth is producing data. Humans are analysing it. Probabilities are being updated, sometimes hourly, in spreadsheets and analysis pipelines that will never make the evening news. A probability advisory is running. and the resolution, whatever it is, will arrive in due course, carried by the ground itself, indifferent to our schedules and our narratives and our desperate human preference for stories that end cleanly. The Earth does not care about narrative closure. The Earth cares about thermodynamics. And we are all living downstream of that indifference. There is a thing I think about sometimes when I look at sequences like this one, which is that every major earthquake in history looked like a puzzle in its final hours before it ruptured. Every fault that broke catastrophically had been sitting there, loaded for decades or centuries or in some cases millennia, and in the final days before it failed, it almost certainly produced subtle signals that, in retrospect, could be read as warnings. Sometimes those signals were noticed in real time and ignored and became part of the tragic history of the event. Sometimes they were not noticed at all and only discovered in the data years later, when careful reanalysis showed that the fault had been speaking before it broke, but no one had been listening in the right way, or with the right instruments, or with the right assumptions about what to listen for. We do not know and cannot know in real time whether we are looking at a fault that is speaking right now, or a fault that has already said its piece and gone quiet. That is the uncomfortable truth that sits under every word of this script. We do not know what this earthquake was yet. That sentence is the truest one I can offer you. The magnitude 7.5 that ruptured off Iwate 36 hours ago might be a standalone event, a significant earthquake that will be remembered for its anomalous aftermath and nothing more, a statistical curiosity that fills a paragraph in a review paper 5 years from now. Or it might be a prelude, a first movement in a sequence whose full scale we will only appreciate when the next movement begins, and whose name future generations will learn the way our generation learned the name Tōhoku. The data we have right now does not distinguish between those possibilities. Only time will, only the Earth will, and neither of them is in any hurry. And so, we watch, we wait. We monitor the signals as they come in, and we update our probabilities, and we hold in our minds the uncomfortable fact that the most important question about this event, what it actually was, cannot be answered by any currently available method except the passage of time. 132 hours, give or take. 3 days of hard-edged attention, in which the Earth will speak and we will listen, and at the end of it, we will know something we do not know now. Not everything, not even most things, but something. And that something will be worth the waiting. The next 72 hours will not tell us what happened. They will tell us what this earthquake actually was. This is Project Nightwatch. Thank you for staying with me through all of it. Keep your eyes on the horizon, and keep your feet ready to move.